Hello, this is our Physics 211 project number 2 by Aaron Hume, Brooks Montoya, and Alexander Johnston.
Our group decided to do the second problem available for this project, which is when the blue block is compressing the leftmost spring at a distance xi. The red block is at rest in the middle of the level frictionless table. The blue block begins to move from rest to the right and collides with the red block in a perfectly inelastic collision. The block system then continues to the right until it reaches the rightmost spring. Our objective for this project was to determine the max distance that the rightmost spring can be compressed by the block system.
Now, before we can actually start solving the problem, we have to go for a little bit of setup so that we can get an understanding of the system that we're dealing with here. Now, to start off with that, first off, we made a free body diagram. This sums all the forces and displays them that are acting on both the block on the left and the block on the right. Now, to start off with the block on the left, the blue one, first off, there's a normal force facing upward, then that's between the block and the table. And counteracting that, there's also the force of gravity acting downwards, which is between the block and the earth. Now, because the block on the left is pressed up against a spring right now, but isn't moving just yet, there's also the force of the spring, which is facing in the right direction, as the spring is up against the left face of the block, and that is between the block and the spring facing to the right. Now, for the block on the right, it only has two forces acting on it, that being the normal force between the block and the table, and the force of gravity, which is between the block and the earth. Now, because throughout this, after the spring is released, blocks are going to start moving and then stop again, there's three main types of both energy and motion that we're going to see here. So we're going to be seeing kinetic energy when the blocks are moving, and the equation for that is 1/2 mass times velocity squared. Potential spring energy, which is, for example, at the start here when the block on the left is pushed up against the spring, and that is given by the equation 1/2 the spring constant times the position of the spring, how far it's moved away from its equilibrium position squared, as well as momentum, which is just momentum equals mass times velocity. Now, there are going to be a couple of assumptions that we make for the situation. The first being that both the springs in the system on the far left and the far right side are ideal springs. Now, what this essentially means is that the springs are massless and that they're not going to be adding to the overall mass of the system. The second one is that we have a frictionless surface here, which means that blocks aren't going to be losing velocity as they're moving due to the force of friction. They're not going to be losing energy. They're all just going to slide around the surface almost as if they were on a near frictionless surface like an ice skating rink. Except in this case, there's no friction, we're not going to be losing any energy, and the blocks are just going to keep sliding along as if there was no force there. And finally, we're also assuming that air resistance does not affect the motion. That almost says the same thing as friction, that as the blocks are moving, the force of air resistance isn't going to affect that at all, and the blocks are just going to move along like that wasn't there. Now we are going to be moving on to the diagrams portion of the solution here. Now here we have two energy diagrams for the block on the left and the block on the right at the initial position for both blocks when the block on the left is pushed up against the spring and the block on the right is not moving. Now the block on the left, as shown by the energy diagram in the bottom left, has no kinetic energy because it's not moving at the moment, but what it does have is potential spring energy, as the block on the left is pushed up against a compressed spring that, when released, it's going to turn that potential spring energy into kinetic energy. But because it hasn't been let go yet, it just has all potential spring energy. Now, block 2, on the other hand, doesn't have any kinetic energy because it's not moving at the moment, and it also has no potential spring energy because it's not pushed up against the spring at the moment. Now, in instance 2 here, when the block on the left has been released from the spring and is moving towards the right, but hasn't just yet come in contact with the block on the right, which is still at rest, the block on the left has all kinetic energy now because it's undergoing motion, and it has no potential spring energy because it is now complete. It's no longer in contact with the spring, which means that the spring can no longer be giving it any potential energy. And the block on the right, as similar from the instance just beforehand, the block on the left hasn't caught up with it yet, so it's not moving. It has no kinetic energy, and it's not pushed up against any springs, so therefore it has no spring potential energy. Now what we've labeled at instance 3, where the block on the left has now come in contact with the block on the right, and they are now moving at their final velocity after the collision. There's actually only one, both blocks are part of one system now, because they're both in contact. And that system is still full of kinetic energy, because both of them are moving in the rightmost direction, but haven't yet come in contact with the spring on the right, so therefore they have no potential spring energy, only kinetic. Now, at what we have labeled instance 4, when both the block on the left and the block of the right have come in contact with the spring and have compressed it a bit from its equilibrium position and are both at rest, the system of block 1 and 2 now has no kinetic energy because they're no longer moving, but they do now have potential spring energy because they came in contact with that spring and compressed it from its equilibrium position, giving the total system of block 1 and 2 no kinetic energy and all potential spring energy.
To find the maximum displacement of the second spring, we first started by solving for the velocity after the blue block was accelerated by the first spring, but before the blue block collided with the red block. Because there is no friction between the blue block and the table, this velocity remains constant until the two blocks collide. To find this velocity, we use the work energy theorem to solve for it. The work energy theorem states that an external force is needed to change the energy in a system. Since there's no external forces on the system, the total energy remains constant. Therefore, the potential energy from the first spring must be equal to the kinetic energy of the blue block after it was accelerated by the spring to its maximum velocity. This is true because there's no other forms of energy in the system than these two at these times, so they are equal to each other. After we obtain this equation, that the potential energy of the spring equals the kinetic energy of the blue block, we solved this equation for the initial velocity of the blue block, and that gave us the initial velocity, which is equal to the square root of the spring constant times the initial displacement of the first spring squared divided by the mass of the blue block. We are calling this the initial velocity as it is the velocity of the blue block before it collides with the red block. After we got the initial velocity of the blue block, we used it to find the velocity of the blue block and red block stuck together after the collision. We used the idea of conservation of momentum for this part. Since momentum is always conserved, the initial momentum must equal the final momentum. This means that the momentum of the blue block before the collision is equal to the momentum of the blue and red blocks stuck together after the collision. By plugging in our initial velocity for this equation, we solve for the final velocity of the system after the collision. This was done by factoring the final velocity out of each mass value on the right side of the equation and dividing each side by the sum of the masses of the blue and red block. This gave us a final velocity value of the two blocks that can be used to find the maximum displacement of the second spring. Now that we have a value for the final velocity, we can solve for the maximum displacement by going back to the work energy theorem. We did the same thing this time as we did to solve for the initial velocity of the blue block, but we plug in our new values instead. We plug in the sum of both block masses and our final velocity that we just calculated. By plugging these values in, it allows us to solve for the maximum displacement of the second spring, which is equal to the initial displacement of the first spring times the square root of the mass of the blue block divided by the sum of both blocks' masses.
Our first section of sense-making for the solution is units. The units of the max distance compressed should be meters. If I plug the correct units into the symbolic solution, the resulting equation is that meters are equals to meters times the square root of kilograms divided by kilograms. The kilogram terms goes to 0 due to the division of the units, leaving meters equals to meters. Thus, the expected units of meters matches the resulting units of meters for the max distance that the spring can be compressed. Using the internet, the approximate distance that a spring can be compressed is anywhere from 1 meter to 2.5 meters. I set the masses of the blocks to appropriate masses of 10 kilograms for the blue block and 5 kilograms for the red block. Plugging these numbers into the symbolic solution, we get 1.5 meters times the square root of 10 divided by 15 kilograms. Simplifying the expression, the distance that the spring can be compressed is approximately 1.22 meters. This result is within the expected and reasonable results for a spring to be compressed. For the last section of sense making, I decided to do a special case analysis by making the mass of the red block infinitesimally small. The expected result of the special case analysis is that the max distance compressed by the spring is equal to the initial compression that the blue block exerts on the leftmost spring. This is the expected result because the mass of the red block would not contribute any more mass to the system of the blocks. Since the table is frictionless and level, there would be no loss of momentum to external forces. As a result, the only contributing factor to the compression of the spring would be the mass of the blue block and the initial compression of the leftmost spring. Plugging in 0 for the mass of the red block causes the square root term to go to 1. Therefore, the xf is equal to xi, which matches the expected result. This project problem is similar to Activity 8-1 that was completed in Studio in Week 8. The similarities to this project compared to the Studio problem is that a block is attached to a spring on a frictionless surface. The differences between these two problems are that the spring is originally stretched in the Studio problem, while the spring in this project was originally compressed a distance xi. Another complexity for our project compared to the Studio problem is the collision of the two blocks. The collision aspect of this problem is similar to Activity 1 in Homework 9, when two astronauts collide into one another. The similarities between these problems are that one object is initially moving with some velocity towards the other before the collision. The differences between these problems are that the project problem involves a perfectly inelastic collision, while the astronaut problem involves an elastic collision since the astronauts do not stick together after colliding. And a representation of each problem are shown below, with the astronaut problem to the left and the Studio problem to the right. Thank you for watching.